Hello and welcome to Lecture 3A on Mechanisms. In the previous lecture videos, we finished off our discussion on multi-view projections in engineering drawings. Combined with the lab lessons, we now have the skills required for solid modeling of new part designs and the creation of corresponding engineering drawings that contain all the information needed for fabrication. These are important skills in engineering design, but recall that there is a lot more to the engineering design process. Engineering design requires the application of math and science principles, decision-making, as well as creativity and innovation. For this course's project, you'll be applying the engineering design process in the context of a mechanical problem, so this video and the next intends to give you a better understanding of some common mechanisms. Specifically, we will look at levers, cams, linkages, and gears. Before we get into specifics, let's consider a broad definition of mechanisms. There are many types of mechanisms, but they all share the same general purpose of creating a mechanical advantage and/or transferring mechanical action. To give you an idea of what this means, let's consider the example of a car with an internal combustion engine that typically turns a crankshaft at a very high speed, thousands of revolutions per minute, or RPM. If we had that engine output directly to the wheels of the car, operation at such a high speed would cause slip at the tires and also insufficient torque. Thus, we need a gearbox, or the transmission of your car, a drive shaft, and a differential, which are all mechanisms to reduce the output speed and increase the output torque, as well as to transfer the mechanical action from the centrally located engine to the wheels of the car. Common examples of mechanisms include cams, linkages, gears, and belt drives, which are all shown to the right of this slide. Even though these types of mechanisms all look very different, they're all just fancy levers, so if we understand levers and torque, we can understand many mechanisms. Since this is the case, let's first review the basic principles of leverage. Levers work according to the principles of torque, which is what causes an object to acquire angular acceleration. Torque is effectively the product of force applied to a lever and the distance of the applied force to the pivot point, or axis of rotation. A simple example of torque is the torque required to open a door. We can consider the door as a lever, and we will look at two cases of applying a force to open the door. Our first case will be if we try to open the door by applying a force at the middle of the door, and the second will involve applying a force twice as far away from the door's hinge at the doorknob. If we need a certain torque to overcome the friction in the hinge and the inertia of the door in order to open it, we can conclude from this formula that we only need half of the applied force at the doorknob than at the middle of the door to apply the same torque. This is a general principle of leverage, which can also be applied to more complex mechanisms introduced on the last slide. We will look at each of these briefly, starting with cams. Cams are fancy levers used to convert uniform rotation to non-uniform rotation, or to non-uniform linear motion. Some examples of cams in common mechanisms include drum pedals, engine throttles, and the camshaft of a combustion engine, which opens and closes the engine valves. So let's dive into how this transformation of motion occurs. Cams rotate about an axle and are contacted by an element called a follower that can only translate linearly. Because cams have a non-uniform radius, the follower's position changes over time in a repeatable pattern as the cam rotates. You may have seen this egg-shaped cam before, but all sorts of cam shapes can be designed to obtain precise follower motion specific to an application of interest. The next mechanism that we will consider is linkages, which are yet another fancy form of lever. Linkages create all sorts of complex motions involving the rotation and translation of links. In some cases, their action even looks similar to that of cams. For instance, this shows a linkage in the crankshaft of a combustion engine, where the firing of the piston drives the continuous rotation of the crankshaft. This pump jack, commonly seen in oil fields, also demonstrates the action of linkages, as does this adjustable mirror. In all cases, linkages respect Newton's third law, where every action has an equal and opposite reaction. Because the forces and motion at pin joints need to be the same, the joints between links impose constraints. This joint geometry, combined with the size of linkages, dictates the resulting motion of linkages, which can lead to very complex motions. For simplicity, we will limit our discussion of linkages to 2D planar analysis. A key aspect of linkage mechanism analysis is consideration of the degrees of freedom. Essentially, we need at least 1 degree of freedom to enable motion. If we consider movement in a 2D plane only, a link by itself has 3 degrees of freedom, 2 translation degrees of freedom in the x and y directions, and 1 rotation degree of freedom. If we have 2 links, then they have 6 degrees of freedom combined, and if we connect them together with a pin, we lose 2 degrees of freedom, because now the 2 links must translate together. If we join the links by a half slider rather than a pin joint, we lose only 1 degree of freedom, and if we put a link on a full slider joint, we lose 2 degrees of freedom, because now the link can only translate in one direction. This is all combined into Grubler's equation for planar analysis of linkages, which determines the number of degrees of freedom remaining in a linkage mechanism given the number of links, pin joints, full joints, and half slider joints, as well as the number of grounded links, which is at least 1. So let's apply this equation to 2 mechanism examples. First, we will look at this triangular linkage. This has 3 links with 3 pin joints, no slides, and we will say that this one white link is grounded. We can plug this information into Grubler's equation, and we will find that this system's degrees of freedom is 0, meaning it will not move. This means it's not actually a mechanism. Instead, it's a truss. Let's consider the second example instead, which is a common type of linkage called a 4-bar linkage. As the name suggests, this 4-bar linkage consists of 4 links with 4 pin joints, no sliders, and 1 grounded link. You might be thinking, wait, I only see 3 links, where is the 4th one? We have the crank link, which is often the input link. We have the coupler link that joins the crank to the rocker, which is often the output link. And our 4th link is actually formed by the 2 grounded points of the crank and rocker. Using Grubler's equation to calculate the 4-bar linkage degrees of freedom, we end up with 1 degree of freedom, meaning that this mechanism can move. So the next question is, well, how does it move? And the answer would be, it depends. Specifically, the linkage motion is dictated by the link proportions, as seen in these 4-bar linkage diagrams. In each of these diagrams, the path of pin joints is traced out in gray, and we can see that combining different crank, coupler, and rocker link lengths gives us either circular paths, arc paths, or some combination of the two. This becomes much more complex to analyze, so we won't go any further into the topic of linkages, but there are many interactive websites that you can use to test out the behavior of different linkage lengths and arrangements, such as this MechDes website that you are encouraged to visit if you want to learn more. For now, we'll move on to our final mechanism discussion, which is gears. Gears are rotating machines that have cut teeth that mesh with the teeth of another gear, and they can be thought of as rotating levers. Specifically, we can think of each tooth like a lever imparting a force on the tooth of another gear, and once that set of teeth rotates out of the way, another set of teeth, or levers, will take its place. If we mesh different size gears together, and knowing that the applied force at the teeth is equal according to Newton's third law, we know that the input and output gear torques will differ, creating a mechanical advantage. Moreover, gears can be used to increase or decrease an input torque and rotational speed, and they can also be used to change the direction of motion. There are many different types of gears, including spur gears, worm and worm gears, helical gears, bevel gears, and planetary gears, whose actions are all animated here. We can see that these different gear types all transform motion differently, where gears like spur gears transform rotary motion to rotary motion on a parallel axis. Other arrangements, like this rack and pinion, can transform rotary motion to linear motion instead, while worm and bevel gears can transform rotary motion to rotary motion on a perpendicular axis. For now, we will focus on spur gears to understand their basic principles of action. Again, spur gears are used to transmit motion from one shaft to another parallel shaft, and they can be identified by their straight-cut teeth, whereby the teeth edges are parallel to the gear's axis of rotation. We see that these two gears are mated or meshed together when their gear teeth are engaged, and the resulting set of two gears is called a gear set. In this gear set, we call the smaller gear the pinion and the larger one the gear, so just be aware of this terminology that we will be using in the rest of the video. Generally, when we combine gears together, we are creating a gearing train. The reasons that we might want to create a gearing train include to change the speed of rotational motion, to create a mechanical advantage by adjusting torque, and or to change the direction of rotation. We'll explore how these gears accomplish this, but first we need to familiarize ourselves with some more gear terminology. One of the most important terms to remember when it comes to gears and gear design is the pitch circle, which is the radius where the gear teeth in a gear set contact tangentially, as shown by the red circles here. The corresponding diameters of these circles are called the pitch circle diameters, and it should be noted that these are neither at the tip nor the base of the gear teeth. Typically in gear design, we can represent simplified gears by drawing just their pitch circles with the knowledge that they must be tangential for meshed gears. The center distance of a gear set is another important consideration in gear design, and it is simply the straight line distance between the center points of two meshing gears, as shown by the blue arrow here. This center distance is equivalent to the sum of gear radii, as measured using the pitch circle, which will come up again in the next video on gear design calculations. Moving on to more terminology, the number of teeth on a gear is represented by the variable z, and is also an important consideration in gear design. For meshing gears in a gear set, the teeth size must be the same for the gears to mesh properly, and we will see later on that the ratio of the number of teeth between meshing gears is directly related to the speed and torque ratio between the gears as well. Face width is another term that simply refers to the front to back distance along a tooth, or essentially the gear thickness, as indicated here in this diagram. Circular pitch, which is not to be confused with the pitch circle, is a measure of the circular distance from a fixed point on one tooth to the same position on the next tooth, as measured along the pitch circle, which is also shown on the diagram. This circular pitch, represented by lowercase p, is calculated as the pitch circle circumference divided by the number of teeth on a gear. So it is a function of pitch circle diameter and the number of teeth. Again, we mentioned that gear tooth size between meshing gears must be the same for them to mesh properly, and we can define gear tooth size using one of two measures. Our first option is the diametral pitch, represented by capital P, which essentially represents the number of teeth per inch. If we have a gear with a large diametral pitch, it will be a fine gear with very small teeth, whereas a small diametral pitch would correspond to a coarse gear with very large teeth. This measure is commonly used in the imperial system since we are dealing in inches, but in the metric system, we specify two size using the module instead. Module is represented by a lowercase m, and it is essentially the ratio of the pitch diameter to the number of teeth, which is like the inverse of diametral pitch. This means that a large module corresponds to coarse gears with big teeth, while a small module corresponds to fine gears with small teeth. We've gone over quite a few terms, but the most important equations to remember that relate the pitch circle diameter d, the diametral pitch p, the module m, and the number of teeth z are summarized here. Since we are working in the metric system, we will use the middle equation, d equals m times z, in gear design calculations. With this terminology and variable definitions out of the way, we can now get to the fundamental law of gearing that explains how gears can increase or decrease torque and rotational speed. This fundamental law of gearing is based on the fact that at the point of contact between two meshing gears in a gear set, the teeth of both gears in the gear set must be moving at the same linear speed. If the linear speed was different, the gears would slip or grind, which would lead to deformation and ultimately to failure. Also, at this point of contact, which is also known as the pitch point, the contact force on each gear must be the same according to Newton's third law, that every action has an equal and opposite reaction. If we know that the linear speed v and the contact force F are the same at the pitch point for gears with different radii, then we can conclude that their rotational speeds omega and their torques tau must be different according to two key physics equations. The first being that linear speed is equal to angular velocity times radius, and the second that torque is equal to the applied force times radius, as we saw before with levers. So let's go through a quick derivation to see how the ratio of gear sizes affects the ratio of angular velocities and torque. First, let's say we have a gear set where the pinion's diameter is labeled d1 and the gear's diameter is labeled d2. We know that the linear speeds v1 and v2 at the point of contact must be equal according to the fundamental law of gearing, and these linear velocities are equivalent to the product of gear angular velocity and radius. If we make this substitution, we end up with omega 1 times r1 is equal to omega 2 times r2, which can be rearranged to relate the ratio of angular velocities to the ratio of gear radii, or equivalently gear diameters. At the end of the day, we end up with omega 1 over omega 2 equals d2 over d1, which tells us that the step in rotational speed from gear 1 to gear 2 is inversely proportional to the step in diameter, meaning if the diameter goes up, then the rotational speed goes down. We can go through the same derivation to relate the torque ratio to the diameter ratio, starting off by equating the contact forces F1 and F2, and knowing that the torque is equal to F times R. Going through the same procedure, we end up with the equation stating that d2 over d1 equals tau2 over tau1, so a step up in diameter also leads to a step up in torque. Of course, one thing we omitted in this derivation is consideration of direction. We only looked at the magnitude of velocities, forces, and torques, but don't forget that the direction of rotation also changes. Now that we have these two equations, you might also note that these ratios are in fact equivalent, and we can give them a name, the gear ratio. We will represent this gear ratio between two meshing gears as a variable I, and all of its equivalent ratios are listed below for a gear set with input gear I and output gear O. The ratio of diameters, radii, angular velocities, and torques are taken directly from the last slide, but these are also equivalent to the ratio of the number of teeth on the output gear to the input gear according to the equation D equals mz, where m, the module, must be the same for meshing gears. We will use these equivalent ratios in gear design calculations in the next video, but for now we've established that a larger output gear diameter yields a smaller output angular velocity and increases the output torque, while a smaller output gear diameter yields a larger angular velocity and decreases the output torque. This wraps up our discussion of mechanisms in this video. We've covered the principle of levers, cams, linkages, and gears, and stay tuned for the next video for more on gear train design.